kind of interesting. 0.003 ounces of blood. That's all you need to analyze someone's blood. We did a, right, Ricky? We did a rat project. We did a lot more than 0.003 ounces of blood, but we didn't really know what we were doing either. But gas chromatography, really powerful. I mean, look at all the things you can analyze. Even you jump down to, where is this? Some opium, right? And see how pure it is, I guess. Forensic science, there's a lot of applications for gas chromatography. What's the mobile phase, Ida, in gas chromatography? What would you say? Because in chromatography, you're supposed to have a stationary phase, supposed to have a mobile phase. What's the mobile phase? Starts with the G. Gas. Gas. All right? The gas is pushing everything through. That's your mobile phase. Almost all gas chromatography utilizes capillary columns. And we'll be talking about those. At the head of this column, when doing GC work, the sample is, what would you say, Andy? You're doing gas chromatography, so that sample needs to be the best word to describe what you're injecting. Vaporized. It's got to turn into a gas. And this is really the limitation of this, because not only does it need to turn into a gas, but it can't degrade on the process, right? Like sugar. Sugar, you can turn sugar and you try to heat it, you know, it might sublime a little bit, but it's going to caramelize. So there's a lot of things you cannot analyze on the GC simply because you can't get it to be vaporized without breaking down. Here's a flow diagram of a GC instrument. What would you think? Well, we're supposed to have a mobile phase, Sabina. Where is this mobile phase going to be supplied? Do you recognize it? Where's Sabina? Oh, there she is. I'm not a very good artist.
Is it like the mobile thing?
Yeah, no. It's the Mickey Mouse looking thing. The Mickey Mouse looking thing is where our mobile phase is. Do you recognize? I don't know. See, I tried to draw it with the, it's called a gas regulator. When you walk in and you see these big, tall metal cylinders, and then there's these two dials, right, on there, two gauges. And one gauge reads the pressure that's coming out of the cylinder, and the other pressure reads what's in the cylinder. So that's really how this thing works, and it comes over to there. So here's your mobile phase. In fact, we use hydrogen gas. So you can label it mobile phase or hydrogen gas, but here's our mobile phase. It has to be a big container of it somewhere under really high pressure. And then again, it has two levels of gauges, one for what's going out and the other one for what's in the tank. Okay, but it's kind of confusing. I'm just going to leap it out. That's the purpose of it. And then you got to know what dials to turn and where to turn where. That's more like for a course for instrumental analysis. But okay. So then in this picture, Kelly, where would you guess, knowing that the mobile phase is connected, where would, how can I don't see how I can really guide you into this. I just pretty much have to draw it, right? We need our capillary column. So draw like 60 meters of this thing. And then where it ends up, right there. All right. So that would be your capillary column. This whole thing here is called the inlet. Okay. So that inlet has a couple jobs to do. One, it has to, you have to have some way to insert your sample, so it has to seal it, right? And then it has to vaporize that stuff and get it out of there. And it has to also be set up where, dang it, oh, whoops, I injected some Coca-Cola and all caramelized. I got to clean it out. So there should be some easy way to handling and cleaning that out. So anyway, so the inlet, you assume, does its job, while the mobile phase container does its job, right? It supplies the mobile phase. And then it comes all over, connected to the inlet. Inlet does its job. It vaporizes what you injected, right? And then it shoots everything down into the column. The column better do its job. And its job is to, what, Gloriana?
Purify?
Well, kind of, yeah. Purify and separate, right? Separate it into its pure components, right? So the column does its job, purifies, yeah, but I think for me, a better picture is separate, right? It separates the mixture into its components, and then everything ends up striking or entering a detector, right? And there's going to be a bunch of those that you can pick from, okay? Now, all of this is in this dashed box, okay? And that dashed box is connected to a computer electronically. The detector had better be connected to the computer, right? The inlet somehow needs to be, let's see, I should draw different colored lines for wires. What color? Maybe I'll make them purple or something, right? Or dash. No, I can't do dash because there already is a dash. Let's make them purple. Computer. So my electrical connections are purple, right? My computer better know when it was injected, so somehow something's got to be in, there has to be some information coming over there. Now this dash box, well, I guess the computer's also, it's also giving you feedback on the mobile phase too to make sure there's something there, but I don't think it's too active because if it runs out, the GC doesn't know it and we can destroy our column. So maybe newer versions are better. But this dash box means that everything is put in a, anybody know? Put it in an oven. And this oven, it can really control the temperature down to tenths of a degree, but change it really rapidly. Over a minute, it can jump 20 degrees. So it's very, very well controlled temperature. So here's a picture. Do you recognize any of this or what it could be? Like you see this big thing in the back? I don't know if you can see it very well, but that's a big what? A big oven. The whole thing's a big oven, but the big thing in the back with these fins, it's a big fan. It's a big fan. So it can remove all that air, or pump in the air. It can change that volume of air temperature really rapidly. Okay, and here's our inlet. Do you recognize the capillary column? Well, yeah, it's that. Yeah, that around the fans. That orange thing. Here's our column, our capillary column. And it's really hard to see. You almost have to be up here where I'm at. Capillary column's coming up, and there it is. It's going to the detector. Right? So it starts over here and ends up going into the detector. So that's the general idea of how a GC works. A common detector is the flame ionization detector. And it's very odd that this actually works. It's just part of nature. If any carbon at a, put it this way, carbon at a really, really, really high temperature atomizes. Not only does carbon atomize, become an atom, but it ionizes itself. All carbon atoms. It's just a property of carbon. You heat up carbon to an extremely high temperature, pretty much the temperature of a hydrogen plasma flame, and it's going to just atomize. So you have little carbon ions. And, well, all these carbon ions have their anions. So what do? You have a big, huge positive voltage here, huge positive voltage that surrounds this flame. So then what do the little negative anions do? Well, they just go, they're collected to those plates, right? And then you get a little induces, you see a very small charge, very small electrical charge. And that's all it's doing. It is burning stuff, but it has to burn things at a very, very high temperature. Otherwise, you don't generate those carbon anions. And then you're not going to see any signal. Okay, so that's essentially how a FID, or flame ionization detector, works. It just ionizes carbon atoms. And is that going to work for everything? No, it's just a property of carbon. Okay, and it's very nice though, because anything organic has carbon in it, so it's very, very applicable. So if you kind of followed what I said, maybe you can answer this question. And FID is actually a blank counter. Carbon. It's a carbon counter. I guess it better would be a carbon atom counter or something, or carbon ion counter, but it's a carbon counter. Okay. Are there some gases that a FID could not detect? What's that? What could it not detect? Neon, argon, good, krypton, all those. But you don't come across those very often. Except, ooh, nitrogen, hydrogen, very good. There's one that will make this detector extremely, extremely useful for analyzing environmental contaminants in our environment. It can't detect H2O. It can't detect water. So imagine you've got a detector that has, if you have aqueous samples, you're looking for, like we did, we did a research project looking for any common drug that you take in our sewer water. Because you take samples before the sewage treatment plant and after the sewage treatment plant. And yeah, what people are saying in the environment, environmentalists, ooh, crazy, crazy. Well, sometimes they know what they're talking about. This stuff is building up in our environment. It's not evaporating, it's not breaking down, because it's built not to. Like ibuprofen, for example, and we found that. We found naproxen too. But the point is aqueous samples, there's no background. It can't just see it. So all it's looking for is your carbon atoms. That's kind of nice. Using a C18 column. We'll talk about what this means later, but it's just describing what the stationary phase is. Very organic-like, very fatty-like. But they're trying to say that gasoline was injected onto a gas chromatograph, inlet temperature of 250, oven temperature of 145. So they did all these things, and they just, they had the oven. So the oven meaning oven's at 145. So that means this big box is at 145 degrees. And they said this inlet was at 250 degrees. Okay, that's fine. Well, they got some results. I mean, they got some peaks. And they're just saying, well, how could this thing be improved? What the question is really getting at is, how do you make these peaks move around? How do you make these peaks move around? And remember, the power of chromatography is whatever this guy is, that's a property of that compound. He is always going to come off at that time as long as you don't change the parameters of the separation. That compound will always come off at that time. Or this compound or that compound. How do you move these guys around? You change the what? Change the temperature. Temperature is the big thing in gas chromatography. That's the only thing you can really change. Because look at all this stuff. I mean, what else could you change? If you want to change the column, you got to tear the whole thing out, put it back in. That's a lot of work. No, I just want to, look at that. All I want to do is make this peak move over here instead of waiting 5-10 minutes for it. You've got 30 of these things to run. So you may like it because you get to sit around on it for 5 minutes and do nothing, but the people that are paying you pretty much $200 an hour or whatever, they're not going to be happy about it. So how can you make this peak go over there? What could you do with the setup that you have? Change the temperature of the oven. At what time? You have this computer. At what time? You can have it change at 10, but why not even have it change even earlier? Right? What is that? It'd be about like around 7 or 8 even. Crank up the temperature. Or would you want to make it lower? There's a good question. Would you want to make that oven temperature higher, or would you want to make that oven temperature lower? And we're going to be talking about that coming up here, but maybe you can imagine it right now. Make it higher. If your sense is higher, you're on the right track. Crank up that temperature around 7 minutes or so. And that last peak is going to elute even faster. Okay?
Would it matter if you changed the inlet?
No. No, it wouldn't. The only purpose of that inlet is to do this. Without those gasoline components degrading. So if you really want that inlet temperature as low as you possibly can get by with, because then to avoid issues. Let's see. Yeah, so inlet temperature really doesn't have much to do with that. Good question. GC capillary columns. When using capillary columns, the analyte's partitioned between the mobile phase and the liquid phase that is immobilized on the walls of the capillary column. There's a lot of words there. Right? Here's what you're after. And it's supposed to be partitioned between the mobile phase and the liquid phase that's on the walls of the capillary column. So here's your capillary column, this stuff, right? Let me change color here. Here's your capillary column, right? The column wall, that's this thing. Well, then you have this liquid layer on the inside. What color can I make that, all right? They coat some liquid on there. That's your mobile phase. All right, sorry, that's your stationary phase. Your mobile phase is a gas blowing through the center of the capillary, right? So this is a hunk of glass, column wall, and then it's coated with your stationary phase, and it's a liquid. Or if they can't get it to coat on the inside walls of that capillary, they'll coat it on little tiny particles and jam them in the tube, in the capillary column. Okay, so there's stationary liquid phase or solid support coated stationary phase. Okay, so kind of like wall coated or stationary coated. But the idea here is that this type of chromatography, which everybody does modern days, is referred to as gas blank chromatography. We're not supposed to call it gas chromatography. We're supposed to call it gas liquid. Very good. Gas liquid chromatography. That's what you're supposed to be saying all the time. Because your stationary phase is a liquid. So you're supposed to be saying gas liquid chromatography. So these capillary columns, they're made of glass. And this lady should be wearing some safety goggles here because glass does break, right? And here's the capillary column in this bag. Okay, and you can bend it. If you bend it too much, it'll break, but it bends. Does glass bend, Andy? Wow, if you take your glasses and all right, that'd be polycarbonate. I bet you can get by. But glass doesn't bend, right? How the heck? Glass, and look at that, and you're passing this thing around. Glass shouldn't be bending. But also, glass shouldn't be what color, Ida? Ida, what color is this stuff? Copperish. Copperish. Well, what color should glass be? All the glass that we know of. It should be clear. So something already is funky going on here. If you make glass extremely pure, glass is made up of what? What is glass? Silicon atoms and a whole lot of oxygen atoms, right? And this crystalline structure. And if you get rid of all the impurities, man, glass bends. You have to get rid of all the impurities, though. Some expensive glass. But you get rid of all the impurities, it also becomes really reactive. This crystalline structure does. It's really reactive with actually oxygen in the air around you. So then when it interacts or you touch it with your finger and get some fingerprint on there, then that little area will break when you bend it. So they have to coat this really pure glass with a polymer, polyimide, and it's orange. Okay. And why polyimide? I guess it's temperature resistant, it's stable, and cheap. So that's kind of what's going on here. Is you get ultra pure glass so it can bend, great, but then you have to coat it with this orange polyimide coating so it won't break on you. Okay, protect it from the oxygen and fingerprints and all that kind of stuff. And it is kind of neat. If you do want to break that and you want it to snap in a certain location, pretty much all you do is just scratch it a little bit and then it'll just snap right off at that point that you scratched it. Let's see. Below is a cross-sectional diagram of a capillary column. See if you can label each part. Okay. The most outside part of this capillary column that's used in gas liquid chromatography is what's this part out here? That's got to be the what? The coating. So you should label that the polyimide coating. Is that poly? And then IMIDE. That's your coating. And then immediately below it would be anybody? The column, the glass, right? The glass, that tube, whatever you want to call it, the glass capillary, the glass tube, the column wall, ultra pure glass, okay? Then the innermost layer is the stationary phase. And it is a liquid. Okay. It's amazing how they make these capillary columns. And I got to see it and push some buttons to make them at, what was that? NASA Langley Research something. But it was pretty neat. But what I don't understand is how they coat the inside of these columns. And I think it's really, secretive. What's that? I don't have any idea. I think they gotta somehow use patented secret process, but it's gotta be blown through. But this is chromatography, so you want this thickness to be the same everywhere. We already talked about eddy diffusion, and to make it extremely uniform, thickness all the way down. Somehow there's some trick to it, and I don't know what it is. The below illustration, you should Google that, but I have never been able to find it out. Okay, here's an illustration of the molecular interaction inside a capillary column. And I say first let's identify it. So you recognize here's our, right? There's your glass. There's your stationary phase. I don't know how well does your print? Yeah, your printout came out pretty good. It looks better than what it does up here. Still can't see it. Okay, but here's the partitioned idea is really well illustrated here, because some of the molecules are in the stationary phase, some of them are in the mobile phase. So that's the exact idea of partition. But partition is a little bit more than that. It means the proportion, right? And these are partitioned quite differently, right? One compound has much more in the stationary phase than the other one. Okay. Anyway, we're saying that this picture is lacking because no dynamic equilibrium is shown to exist between the blank and blank phases. What would be the best words to put in there, Desiree? What two phases is it trying to illustrate? The stationary phase and the mobile phase. Exactly. It's trying to illustrate that there's no dynamic equilibrium between the stationary phase and the mobile phase. Now, what does it mean, dynamic equilibrium? Kelly, what is it talking about? Dynamic. It's trying to say that this is supposed to be a dynamic equilibrium. And I guess I could make it dynamic if I made it one of those animated GIF files. So I have things moving all the time, right? That they're entering the mobile phase at the same rate that they're leaving the mobile phase. Sorry, they're entering the stationary phase at the same rate they're leaving the stationary phase, or leaving the mobile phase at the same rate they're entering the mobile phase. Either way, make it dynamic. So that this is just a static image, so you can't make it dynamic. But in the below illustration, bands of two compounds are shown. So you've got red molecules and you've got another analyte with blue triangles. Which compound would you say, Monica, has a higher affinity for the stationary phase?
The red dots.
The red dots. Exactly. So the whole idea with chromatography is like dissolves like. So the red dissolves much, much better in the stationary phase. So the red must be much more chemically like the stationary phase. Like dissolves like. The blue triangles, not so much. Right? Their affinity for the stationary phase isn't that high. So their partitioning is much higher in the mobile phase. Okay. So she said the red dots. Which will elute first? Brandy, which compound will elute first? I guess you kind of got to see the arrows. Flow of helium. What's that? Yeah, the blue, because they're trying to say helium is your what phase? Mobile phase. So it's going from left to right. So yeah, so the blue triangles will elute first. How could I change the partition? Ricky, I could change the stationary phase. That means I got to change the whole column out. That's one way that I could change this partition, right? In other words, the amounts in the mobile phase and the stationary phase. What else could I do to change the partition?
Could you change the mobile phase?
Problem with the mobile phase, and it wouldn't really matter anyway, because the mobile phase, its sole purpose is to push everything through. And then that mobile phase, all you got is this big cast iron tank. Oh my goodness, it wouldn't do you much. It wouldn't be worth the effort to change it, and the effect of it wouldn't be that helpful anyway.
Just the temperature, then?
Temperature. That's it. That's what I'm trying to get you to ingrain in your brains here. You mess with temperature in gas chromatography if you want to change the partition and get more into the mobile phase. And there's some different types of capillary different types of columns. They call them packed and capillary. This is just, you can kind of see it's already scanned and it's old because nobody really does this anymore. Because and this is why. I mean, look at the results. You get nice pretty peaks and a better resolution with capillary columns. So, packed column is almost like liquid chromatography. You just pack a bunch of solid material in a tube. Okay. Effective temperature on retention time. There's a lot of information here, but I think the main things I want you to see, here's a chromatogram at 75. Here's a chromatogram at 110. Here's a chromatogram at 130. And that's all they're trying to get you to see is forget about what the compounds actually are. Just realize, look at what happens as you crank up the temperature. Things elute what? Faster. Now, C12 just means some compound that had 12 carbons in it. And did it always elute last? Seems like it, yeah. So, right, doesn't look like it's always last. That means that stationary phase is probably what? Very, what type of material would that be? Something very, very similar to C12. And this is where things are kind of odd. I mean, it just takes getting used to. How something with 12 carbons is very different than something with 8 carbons. And this idea of the degree of being organic, or some solvents are more organic than others, that whole type of talk is just something that you can only get used to by injecting samples and seeing their effect. But the C12 is extremely organic, is the words that they would say, because the stationary phase is probably this big, long chain, maybe something like, and we'll talk, well, pictures of them, but much more organic than C12 even.
What if the stationary phase is something closer to 8 carbons?
I would say, if you change it to something closer to C8 column, I think that the thinking that is there is, if you have something with 8 carbons on it, is that what you would classify as an organic compound? Or is its organicness pretty high? Not as high as C12, but it's still pretty dang organic. It's not like methanol or ethanol or something like that. It doesn't have any OH groups, or it's still very, very nonpolar. And they like to use the words organic instead of polarity, but that's fine. So C8 is very, very nonpolar. C12 is still going to come out last because it is the most nonpolar out of all of them. But nonpolar doesn't really seem to fit. C12 and C8, they're both nonpolar. That's why I think they talk more about words of organic and number of carbons. So C12 is a much more organic compound than C8. You have a C8 column, that's an organic column. C12 is still the most organic, it should still come out last.
What kind of column are they showing there, like a C18? Or
Now, it's going to be really, it could be. Now, funky things do happen though. You would think, and I'm just guessing to answer you, odds are I'm 85%, maybe 90% right. But funky things happen with temperature, that these affinities can switch on you. All of a sudden, above 110 degrees, C8 comes out after C12. Some weird things can happen like that, but it's not very often. But just be aware that it is possible. So the inlet. So we are talking about, where'd it go? Our inlet. We're talking about this part right here. Let's take a closer look at it. Now, wouldn't it be nice, you're injecting that urine sample, and that it's kind of gross, and the dude, oh man, I don't want to dilute this because I got to touch it even more, right? Look at all the, well, why not have a little, the instrument itself, the gas chromatograph, why inject everything? Just inject 1/100th of it. Inject a 200th of it. So much easier. Exactly. That's what this inlet allows you to do. And that's why they call it a splitless injector or inlet. So splitless is when, hey, that entire urine sample goes into the, right? Gets vaporized, goes into your column, right? That's what's coming out down here. That's your capillary column. If you split it, no. A lot of that is just going to, there's tubes on the GC that are going out along the wall and back up the hood in the back of the room. And that's where a lot of that stuff would go. So, and you set it on the computer. So all that stuff would shoot out the split outlet. Now you have to insert your sample in here somewhere, right? And you see, can you see this is where that needle goes? How do you draw a needle? Something like this, right? That's my needle, right? But it has to puncture. And you would think, and I still don't, maybe it's just, maybe they have found it, but it's super expensive. but I don't think so. Rubber is all we have to seal this system. And it causes a lot of problems. Why is this guy beeping? It causes a lot of problems. Oh, it causes a lot of problems because if you go to Sam's, you go down the tire aisle, what do you smell? Rubber. You smell the tires. And it smells, well, depending on who you are, whether it's good or not. But it's a real problem. And realize how, I can't relate to you how extremely sensitive these instruments are. They're extremely sensitive. So just what's coming, if you take a little piece of that rubber tire and heat it a gazillion times trying to drive off all this gas, and you can't even smell it anymore, you heat it a gazillion times more, it's still permeating gases. That's just something rubber does. So this whole time, you have to blow mobile phase out the septum purge outlet. That's what's going on here. This mobile phase is just being blown out because this is your rubber septum. That's your rubber septum. Up on top, this thing is your rubber septum. Okay. So we have a glass liner. In case someone does inject Coca-Cola and it caramelizes, you can just pop it out and throw it away. That's what's in this bag are some glass liners and some rubber septa. Okay. And then your splitless inlet. So the gas has to, or let's not call it that. Let's call it the mobile phase inlet. Right, because your inlet, your mobile phase is going to enter this entire apparatus. A lot of it's going to, right? Well, here's the answer right here. What are the 3 ways that a sample can actually leave the inlet, according to this? There's 3 ways. The septum, yeah, I guess it could, right? And you don't even want your sample to go out that septum purge, but it could go out that way. I don't see why it wouldn't. I'd say that's one. Good one. Where else? The split outlet, if you're using that. And then the capillary column. There it is. There's your 3 ways.
Where is it again?
Okay. So what is sample overload? How can it be avoided? Sample overload is you're doing that ibuprofen study in Elmendorf lake water, or any pharmaceutical drug is what you're looking for. And, oh, man, I want to inject as much water as I can. Well, how much can you inject and not overload your inlet? Because this guy can only, right? Remember PV equals nRT? There's only a certain volume here. You can only vaporize so much, and then you're done. So there's a computer program, and it's very easy to use. You just plug in all the parameters, the inlet size, all that stuff, your temperature, and it tells you how much you can inject, okay, to avoid those issues. So we're out of time, and we're done anyway. So have a good day.